Introduction to Bitcoin Contracts. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're embarking on a comprehensive journey through Bitcoin's contract capabilities. When most people think of smart contracts, they immediately think of Ethereum or other smart contract platforms. However, Bitcoin has had programmable contract capabilities since its inception in 2009. These capabilities are built into Bitcoin's core design through a stack-based scripting language called Bitcoin Script. While Bitcoin's approach to contracts is different from account-based smart contract platforms, it offers unique advantages in terms of security, simplicity, and predictability. Throughout this presentation, we will explore the full spectrum of Bitcoin's contract features, from the basic scripting language that powers every transaction, to advanced concepts like multi-signature wallets, time-locked contracts, hash time-locked contracts used in the Lightning Network, Taproot's privacy improvements, discrete log contracts for financial derivatives, and future proposals like covenants. We will examine how these technologies work, their use cases, their limitations, and how they are evolving. By the end, you will understand that Bitcoin is far more than just simple peer-to-peer payments and that its contract capabilities, while different from Ethereum, enable sophisticated financial applications while maintaining Bitcoin's core values of security and decentralization. Bitcoin Script, the foundation. Bitcoin Script is the fundamental programming language that underlies every Bitcoin transaction. It's not a general-purpose programming language like Solidity or JavaScript. Instead, it's a specialized stack-based scripting language designed specifically for defining conditions under which Bitcoins can be spent. The language is intentionally simple and limited in scope, which is a feature, not a bug. This simplicity makes Bitcoin Script easier to audit for security vulnerabilities and reduces the attack surface compared to Turing-complete languages. Every Bitcoin transaction contains scripts. The output script, called script pub key, defines the conditions that must be met to spend the coins. The input script, called script sig, provides the data that satisfies those conditions. When a transaction is validated, nodes concatenate the script sig and script pub key and execute the combined script. If the script executes successfully and leaves a true value on the stack, the transaction is valid. Bitcoin Script operates using a stacked data structure, which is a last-in first-out collection of elements. Operations called opcodes manipulate data on this stack. The language includes opcodes for arithmetic operations, cryptographic functions like hashing and signature verification, conditional logic, and stack manipulation. Importantly, Bitcoin Script is non-Turing complete, meaning it cannot contain loops and will always terminate. This prevents infinite loops and makes resource consumption predictable. The language also lacks the ability to maintain state between transactions, which is fundamentally different from account-based smart contract platforms. How Bitcoin Script works. To understand Bitcoin Script, we need to understand stack-based execution. Imagine a stack of plates where you can only add or remove plates from the top. Bitcoin Script works the same way with data elements. When you execute a script, you're pushing data onto the stack and using opcodes to perform operations on that data. Let's walk through a simple example. The most common Bitcoin transaction type is pay-to-public key hash, abbreviated as P2PKH. In this transaction type, the script public key contains instructions that essentially say, to spend these coins, you must provide a public key that hashes to this specific hash value, and you must provide a valid signature from the corresponding private key. When someone wants to spend these coins, they create a script signature containing their signature and public key. The validation process concatenates these scripts and executes them step by step. First, the signature is pushed onto the stack, then the public key is pushed onto the stack. Then the script public key executes, which first duplicates the public key, hashes it, and compares it to the required hash. If they match, it proceeds to verify the signature against the public key. If the signature is valid, true remains on the stack and the transaction is accepted. This might seem complex, but it provides powerful flexibility. The person sending Bitcoins can define arbitrary conditions for spending, and the recipient proves they can meet those conditions. This is the foundation upon which all Bitcoin contracts are built. Bitcoin script structure and execution. Let's examine the technical structure of Bitcoin script more carefully. Every transaction output contains a script pub key that defines spending conditions. Every transaction input contains a script sig that provides the solution to those conditions. During validation, these scripts are combined and executed on a virtual stack machine. The execution is deterministic, meaning the same script with the same inputs always produces the same result. This determinism is crucial for consensus because every node must agree on transaction validity. Bitcoin script includes several categories of opcodes. Constant opcodes push data onto the stack. For example, op-push data which pushes bytes onto the stack, or specific number constants like opus 0 through opus 16. Flow control opcodes provide conditional execution. For example, op-if, op-else, op-end if which create conditional branches, and op-return which terminates execution and marks the output as provably unspendable. Stack manipulation opcodes rearrange data, including op-dup which duplicates the top stack item, op-drop which removes the top item, op-swap which swaps the top two items, and many others. Arithmetic opcodes perform mathematical operations like op-add, op-sub, op-equal for equality checks, and various comparison operators. Cryptographic opcodes are perhaps most important, including op-hash 160 which performs SHA-256 followed by RIPEMD 160, op-check sig which verifies an ECDSA signature, and op-check multi-sig which verifies multiple signatures. There are also time lock opcodes like op-check lock time verify and op-check sequence verify which enable time-based contracts. Understanding these opcodes is essential for understanding what kinds of contracts Bitcoin can execute. Standard transaction types. Bitcoin scripts flexibility allows for infinitely possible scripts. However, in practice, the network standardizes on several common transaction types for security and efficiency. The most prevalent is pay-to-public key hash, or P2PKH, which we discussed earlier. This requires the spender to provide a public key matching a specified hash and a valid signature. About 40 to 50% of Bitcoin transactions historically use this format. Another important type is pay-to-script hash, or P2SH, introduced in 2012 through BIP 16. P2SH allows complex redemption conditions to be hidden behind a hash. Instead of putting the entire script in the output, you just include the hash of that script. When spending, you reveal the actual script and provide data satisfying it. This enables complex contracts without increasing blockchain bloat, and shifts the fee burden to the spender rather than the sender. P2SH is commonly used for multi-signature wallets and other advanced scripts. Pay-to-witness public key hash, or P2WPKH, and pay-to-witness script hash, or P2WSH, are SegWit transaction types introduced in 2017. These move the signature data into a separate witness structure, providing a transaction malleability fix and an effective block size increase. Pay-to-Taproot, or P2TR, activated in 2021, is the newest standard type. Taproot uses Schnorr signatures and allows complex spending conditions to look identical to simple payments, greatly improving privacy. It enables a tree of alternative spending conditions where only the executed path is revealed. These standard types represent the evolution of Bitcoin's contract capabilities, each building on previous innovations while maintaining backward compatibility. Multi-signature contracts. Multi-signature contracts, commonly called multisig, are one of Bitcoin's most important contract features. A multisig contract requires multiple parties to authorize a transaction before funds can be spent. The most common format is M of N multisig, where M signatures out of N possible signers are required. For example, a 2 of 3 multisig requires any 2 out of 3 designated parties to sign. This has numerous practical applications. Businesses use 2 of 2 multisig between partners to ensure both parties must approve expenditures, preventing unilateral access to company funds. Security-conscious individuals use 2 of 3 setups where they control 2 keys in different locations and a trusted third party holds a backup key. This provides redundancy if one key is lost while preventing the third party from stealing funds alone. Cryptocurrency exchanges use complex multisig setups with 3 of 5 or higher thresholds, distributing keys among multiple executives and securing them in different geographic locations. This makes theft or internal fraud much more difficult. Bitcoin's OP-check multisig opcode natively supports multisig, allowing up to 15 signatures. In practice, most multisig is implemented through P2SH for better efficiency and privacy. The multisig script is hashed and the hash is published on-chain. Only when spending do you reveal the actual multisig requirements and provide the necessary signatures. This keeps the blockchain lean and hides the security setup until coins are moved. Multisig represents a significant improvement over traditional financial systems where single points of failure are common. It enables trustless collaboration and improved security through distributed control. Multi-signature implementation. Implementing multi-signature contracts in Bitcoin requires understanding both the opcodes involved and the practical structure. A basic multisig script uses OP-check multisig, which takes M signatures, N public keys, and verifies that at least M of the provided signatures correspond to the public keys. The script structure for a 2 of 3 multisig looks like this. First, the number 2 is pushed to indicate the threshold. Then 3 public keys are pushed to the stack. Then the number 3 is pushed to indicate total signers, followed by OP-check multisig. When spending from this script, you provide 0 as a dummy value due to an off by 1 bug in the original implementation. Then provide 2 valid signatures corresponding to 2 of the 3 public keys. Modern implementations typically wrap multisig in P2SH addresses for efficiency. To create a P2SH multisig, you first construct the multisig redeem script, then hash it using SHA-256 and RIPEMD-160 to create a 20-byte hash. This hash becomes the P2SH address. The output script is very simple. OP hash 160, the 20-byte script hash, OP equal. When spending, you provide the signatures, then the full redeem script. The network hashes your provided script and verifies it matches the hash in the output, then executes the script with your signatures. This elegant design means complex multisig setups are indistinguishable from regular transactions on the blockchain until they are spent. Recent developments with Taproot enable even more efficient multisig through MASIG or MASIG2, which aggregates multiple signatures into a single signature that appears identical to a single key signature. This provides massive space savings and perfect privacy. Time lock contracts. Time lock contracts enable Bitcoin transactions that cannot be spent until a specific time or block height is reached. This temporal dimension adds powerful capabilities for escrow services, vesting schedules, inheritance planning, and payment channels. Bitcoin supports 2 types of time locks: absolute time locks and relative time locks. Absolute time locks specify an exact time or block height before which funds cannot be spent. This is implemented through the nLock time field present in every transaction, combined with the OP-check lock time verify opcode, abbreviated CLTV. When you create a transaction with nLock time set to a future block height or Unix timestamp, nodes will not accept that transaction into the mempool or include it in blocks until that time arrives. CLTV provides script-level enforcement of time locks, allowing individual outputs to have different time constraints. Relative time locks specify a delay relative to when the output was confirmed on the blockchain. This is implemented through the N-sequence field and the OP-check sequence verify opcode, abbreviated CSV. For example, you might create an output that can only be spent 144 blocks after it was confirmed, roughly equivalent to 1 day. Relative time locks are particularly useful in payment channels and state channels because they allow parties to establish time-based recourse mechanisms. These time lock features enable sophisticated contract arrangements that were previously impossible. You can create transactions today that ensure funds become available to beneficiaries at a future date, create recurring payment schedules, implement trustless escrow where funds return if conditions aren't met within a timeframe, or build complex multi-stage contracts with different parties gaining control at different times. Time-locked contracts. Time-locked contracts, universally known as HTLCs, combine cryptographic hash locks with time locks. These create conditional payments that form the foundation of the Lightning Network and atomic swaps. An HTLC is a contract that states these coins can be spent in one of two ways. First, if you can provide data that hashes to this specific hash value before a certain time, you can claim the coins. Second, if that time expires and the secret has not been revealed, the original sender can reclaim the coins. This seemingly simple construction enables incredibly powerful capabilities. The hash lock ensures that only someone possessing the secret preimage can claim the funds. The time lock ensures that if the recipient does not claim the funds, they eventually return to the sender, preventing funds from being locked forever. HTLCs enable atomic swaps, which are trustless cryptocurrency exchanges between different blockchains. Imagine Alice has Bitcoin and Bob has Litecoin, and they want to swap. Alice creates an HTLC on Bitcoin that pays Bob if he reveals a secret before 24 hours. Bob creates a corresponding HTLC on Litecoin that pays Alice if she reveals the same secret before 12 hours. Alice knows the secret, so she claims Bob's Litecoin by revealing it. Bob sees Alice reveal the secret on the Litecoin blockchain, so he uses that same secret to claim Alice's Bitcoin. Either both transactions complete or both fail, making it atomic. In the Lightning Network, HTLCs enable routing payments through intermediate nodes without trusting them. Each hop in the route is an HTLC, and revealing the preimage cascades back through the route, settling all HTLCs simultaneously. This elegant mechanism enables Bitcoin's Layer 2 scaling solution. HTLC structure and implementation. Understanding the precise structure of HTLCs helps clarify how they enable trustless conditional payments. An HTLC script contains two spending paths implemented through conditional branches. The first path checks whether the spender can provide data that hashes to a specific hash value, and also includes a signature check to ensure only the intended recipient can claim using this path. This path typically looks like OP_IF, OP_hash160, the required hash value, OP_verify, the recipient's public key, OP_check_sig. The second path is the timeout path, which becomes available after the time lock expires. It checks that enough time has passed and verifies the sender's signature for reclaiming the funds. This path looks like OP_else, the timeout value, OP_check_lock time verify, OP_drop, the sender's public key, OP_check_sig, OP_end if. When the recipient wants to claim the funds, they provide the hash preimage and their signature, which triggers the first conditional branch. When the timeout expires and the recipient hasn't claimed, the sender provides their signature along with a flag to trigger the second branch. The security of HTLCs relies on the cryptographic properties of the hash function. It must be computationally infeasible to find a preimage from the hash without knowing the secret. Bitcoin uses SHA-256 or hash160 for this purpose, both of which are considered cryptographically secure. The time lock must be carefully chosen. In atomic swaps, the time locks must be staggered such that each party has sufficient time to respond before the next party's time lock expires. In Lightning Network, time locks decrease along the payment route to ensure upstream nodes can reclaim funds if downstream nodes don't settle. Lightning Network payment channels. The Lightning Network is Bitcoin's most successful Layer 2 scaling solution, enabling millions of transactions per second with near-instant finality and minimal fees. It works by creating payment channels between parties using sophisticated Bitcoin contracts. A payment channel is a multi-signature address where both parties lock funds. Instead of broadcasting every transaction to the blockchain, parties exchange signed transactions off-chain that could be broadcast at any time. These transactions represent the current balance state between the parties. The channel uses commitment transactions, which are pre-signed transactions that either party can broadcast to close the channel and claim their share. Each commitment transaction includes time locks and revocation mechanisms to prevent old states from being broadcast fraudulently. When you want to send payment to someone you don't have a direct channel with, the Lightning Network routes your payment through intermediate channels using HTLCs. Imagine you want to pay Dave but only have a channel with Bob, who has a channel with Carol, who has a channel with Dave. You create an HTLC paying Bob if he reveals a secret. Bob creates an HTLC paying Carol with the same secret hash. Carol creates an HTLC paying Dave. Dave generates the secret and reveals it to claim from Carol. Carol uses that secret to claim from Bob. Bob uses it to claim from you. The entire payment resolves atomically. Channel updates use penalty mechanisms to discourage cheating. When you update the channel state, you revoke the old state by giving the counterparty a revocation key that would let them claim all funds if you broadcast that old state. This ensures both parties only broadcast the most recent state. Taproot and MAST. Taproot, activated in November 2021 through BIP 341. Represents the most significant upgrade to Bitcoin's contract capabilities in years. Taproot combines several innovations including Schnorr signatures, MAST, which stands for Merkleized Alternative Script Trees, and new script versioning. The primary benefit is that complex contracts can look identical to simple single-signature payments, dramatically improving both privacy and efficiency. Taproot outputs commit to a public key and optionally to a Merkle tree of alternative spending scripts. In the simple case where parties cooperatively agree, spending just requires a signature from the committed key, appearing exactly like a regular payment. Nobody can tell if the output could have been spent through complex alternative conditions. If parties cannot cooperate, any script from the Merkle tree can be revealed and executed, but only that specific script branch is revealed, not the entire tree. MAST is crucial here. Instead of putting multiple alternative spending conditions in a single script where all conditions are visible, MAST organizes them in a Merkle tree. Each leaf is a different spending condition. When spending, you only reveal the specific branch you are using plus the Merkle proof showing it was committed in the tree root. This scales much better than previous approaches. A contract with 100 different spending conditions would previously require all 100 to be visible on-chain. With MAST, only one condition plus a logarithmic-sized proof is revealed. Schnorr signatures replace ECDSA and enable signature aggregation. Multiple parties can create a single signature that proves all of them signed, indistinguishable from a single party signature. This makes multisig more private and efficient. Key aggregation using MuSig2 enables collaborative custody without revealing the multisig structure on-chain. Taproot structure and benefits. The technical structure of Taproot outputs demonstrates its elegance. A Taproot output is a pay-to-Taproot or P2TR output containing a 32-byte Schnorr public key. This key is actually a tweaked key computed as the internal key plus a tweak derived from the Merkle root of possible script paths. When spending via the key path, you provide a single Schnorr signature for the tweaked public key. The signature verification equation confirms the signature is valid. This is the cooperative case and it is completely indistinguishable from any other Schnorr signature. Observers cannot tell if alternative scripts existed. When spending via the script path, you reveal the internal public key, the specific script you are executing, and a Merkle proof showing this script was committed in the tree. The verification process recomputes the tweaked key from the internal key and Merkle root, confirms it matches the output key, then executes the revealed script. Only the executed script path is visible, maintaining privacy for unused alternatives. Taproot brings several major benefits. Privacy improves because multisig, time locks, and complex contracts all look like regular payments. Efficiency improves through smaller signatures, signature aggregation, and only revealing used script branches. Flexibility improves because script trees can be arbitrary depth with any combination of conditions. Multisig becomes much cheaper through key aggregation. Future upgradability is built in through script versioning, making future soft forks easier to deploy. Taproot enables more sophisticated contracts while making them less visible, a rare combination of enhanced privacy and enhanced functionality. This upgrade positions Bitcoin for more advanced smart contract applications while maintaining its security and decentralization properties. Discrete Log Contracts. Discrete Log Contracts, abbreviated as DLCs, represent a breakthrough in bringing Oracle-based smart contracts to Bitcoin with strong privacy properties. Proposed by Taj Dria in 2018, DLCs enable two parties to create contracts based on future events without revealing the contract terms on the blockchain. The Oracle signs messages about real-world events, and parties use these signatures to settle contracts. The brilliance of DLCs is that the Oracle does not know what contracts exist or how parties are using its signatures. Here is how it works. An Oracle commits to signing a message about a future event, like the price of Bitcoin on a specific date. Two parties create a contract based on possible outcomes. For each possible outcome, they pre-create a transaction that distributes funds according to their agreement. These transactions are not broadcast initially. The Oracle publishes its signature when the event occurs. Whichever party wins according to the event outcome can complete the corresponding transaction using the Oracle signature. The Oracle's signature acts as a key that unlocks one of the pre-negotiated outcomes. The cryptographic innovation uses adapter signatures. These are partially complete signatures that can be completed only with specific secret data. In this case, the Oracle's signature. The parties exchange adapter signatures for all possible outcomes. When the Oracle signs the event result, the winning party can complete their adapter signature and broadcast the winning transaction. DLCs enable numerous applications, including futures contracts on asset prices, sports betting where the Oracle reports game results, insurance contracts that pay out based on verifiable events, prediction markets on political or economic outcomes, and hedging arrangements for businesses exposed to price volatility. DLC architecture and privacy. The architecture of discrete log contracts demonstrates sophisticated cryptographic engineering. The process begins with Oracle attestation. An Oracle commits to attesting to a specific event by publishing a commitment to the public key it will use for signing. Parties then negotiate their contract. They agree on outcomes and payouts, such as if Bitcoin price is above 50,000, Alice gets 90%, otherwise Bob gets 90%. For each possible outcome, they create a contract execution transaction or CET. These CETs distribute the funds according to the agreed terms for that outcome. The funding transaction locks funds into a 2-of-2 multisig address controlled by both parties. Here's where adapter signatures become crucial. For each CET, both parties create adapter signatures. These are signatures that are almost valid but missing one piece of information, specifically the Oracle's signature on the corresponding outcome. Both parties exchange these adapter signatures. When the event occurs, the Oracle publishes its signature. The party who would win under that outcome can now complete their adapter signature using the Oracle signature, making it a valid signature that completes the CET. They broadcast this CET and claim their payout. The privacy properties are remarkable. On the blockchain, only the funding transaction and one CET appear. The funding transaction looks like any 2-of-2 multisig. The CET looks like a regular transaction. Nothing reveals that an Oracle was involved, what the event was, what other outcomes were possible, or even that a DLC existed. The oracle only sees requests to sign a message. It doesn't know what contracts depend on its signatures or how much money is at stake. This prevents oracle manipulation and maintains user privacy. RGB and client-side validation. RGB is a revolutionary approach to smart contracts on Bitcoin that moves most contract logic off-chain through a concept called client-side validation. Rather than having all nodes validate all contracts as in Ethereum, RGB has only contract participants validate the contract state. The Bitcoin blockchain is used only for commitment anchoring and preventing double spending, not for executing contract logic. This dramatically improves scalability and privacy. RGB contracts define state transitions through a directed acyclic graph of operations. Each operation references previous operations and produces new state. The contract history forms a chain, but only participants need to know the full history. The Bitcoin blockchain contains only cryptographic commitments to state transitions, typically as 32-byte hashes embedded in transaction outputs. When you receive RGB assets, the sender provides you with the full state history proving the asset's provenance. You validate this history yourself according to the contract's rules, confirming all state transitions were valid. If validation passes, you accept the asset. When you transfer it, you create a new state transition, commit it to a Bitcoin transaction, and provide the recipient with the updated history. RGB enables sophisticated smart contracts including token issuance for fungible assets, non-fungible tokens or NFTs, complex DeFi protocols like decentralized exchanges, algorithmic stablecoins, lending protocols, and even potentially privacy-preserving computation. The benefits over on-chain smart contracts are substantial. Scalability improves because the blockchain only stores commitments, not full contract data. Privacy improves because only participants see contract details. Flexibility improves because contract schemas can be complex without blockchain limitations. Bitcoin security is inherited because double spending is prevented by Bitcoin consensus. RGB represents a different philosophy, leveraging Bitcoin's security while moving complexity off-chain. Covenant proposals. Covenants are a class of proposed Bitcoin contract features that would allow scripts to restrict how coins can be spent in future transactions. Currently, Bitcoin scripts can validate the current transaction input, checking signatures and other conditions. Covenants would enable scripts to impose constraints on the outputs of the spending transaction, essentially placing restrictions that persist across transactions. This has been a topic of intense research and debate in the Bitcoin community. Several covenant proposals exist. OP_CHECKTEMPLATEVERIFY or CTV, proposed in BIP 119, allows a script to commit to a specific template for spending transactions. The script specifies a hash of the transaction structure, and the spending transaction must match that template. This enables use cases like congestion control where you pre-commit to a tree of transactions that can be broadcast later. Vaults where coins can only be spent through a specific withdrawal process with time delays for security. Payment pools where groups of users share UTXOs efficiently. And non-interactive channel creation for Lightning Network. Another proposal is OP_CHECKSIGFROMSTACK or CSFS, which verifies a signature on arbitrary data rather than the transaction itself. This enables more flexible covenant constructions. SIGHASH_ANYPREVOUT is a new signature hash type that enables signing transactions without committing to specific previous outputs, useful for L2 Lightning channel updates. More powerful but contentious proposals include OP_covenant and general recursion capabilities. These would enable Turing-complete contracts on Bitcoin, similar to Ethereum. However, they raise concerns about complexity, attack surface, and philosophical alignment with Bitcoin's design principles. The debate centers on balancing enhanced functionality against increased complexity and potential security risks. Covenant use cases and concerns. Understanding covenant use cases helps clarify why they are desired and why they are controversial. Vaults are one of the most compelling applications. A vault is a contract that enforces a time-delayed withdrawal process, providing defense against theft. Coins in a vault can only be moved through a specific multi-step process. First, you initiate withdrawal to a destination address. This broadcasts a transaction but does not immediately transfer coins. Instead, there is a mandatory waiting period, perhaps 24 hours or a week. During this period, you can cancel the withdrawal if you detect unauthorized access. After the waiting period, you complete the withdrawal. Covenants make this possible by ensuring the first transaction can only send coins to the time-locked intermediate stage, and that stage can only send to your approved withdrawal address or back to the vault. Payment pools enable groups of users to share a single UTXO, reducing blockchain space usage. Covenants allow any member to exit unilaterally through a pre-defined tree of transactions, improving efficiency for coordinated multi-user wallets. Congestion control batches multiple payments into a tree structure that can be partially revealed as needed. Instead of creating 100 separate transactions immediately, you create one transaction committing to a tree, then only expand branches as recipients claim. Channel factories for Lightning Network enable creating multiple channels from a single on-chain transaction, dramatically improving Lightning scalability. However, covenants raise concerns. Increased complexity could introduce bugs or vulnerabilities. Some designs could enable recursive covenants that propagate restrictions indefinitely, potentially creating unmovable coins or unwanted coin characteristics. There are questions about whether covenants fundamentally change Bitcoin's properties. The community carefully weighs these trade-offs, seeking covenant designs that enable valuable use cases while maintaining Bitcoin's security and principles. Bitcoin contracts versus Ethereum smart contracts. It is valuable to compare Bitcoin's approach to contracts with Ethereum's approach, understanding their different philosophies and trade-offs. Bitcoin uses a UTXO model where coins are discrete objects that are consumed and created. Ethereum uses an account model with persistent state stored on-chain for each contract. Bitcoin script is non-Turing complete, intentionally limited to prevent complexity. Ethereum's Solidity is Turing complete, enabling arbitrary computation. Bitcoin contracts are stateless, meaning each script execution is independent. Ethereum contracts maintain state variables that persist across calls. Bitcoin optimizes for security and predictability. Every operation has defined resource costs. Scripts cannot loop indefinitely. The limited opcode set reduces attack surface. Ethereum optimizes for expressiveness and flexibility. You can implement complex logic, but this introduces risks like reentrancy attacks, integer overflows, and unbounded resource consumption. Bitcoin's UTXO model makes parallelization easier because UTXOs are independent. Ethereum's account model requires sequential processing of transactions affecting the same accounts. Bitcoin privacy is better by default because contracts are often hidden behind hashes until spent. Ethereum contracts and their interactions are fully visible on-chain. Bitcoin's Layer 2 solutions like Lightning move complexity off-chain. Ethereum tends to put more logic on-chain. Neither approach is objectively superior. Bitcoin's conservative design prioritizes security for a global monetary system. The limited feature set prevents certain classes of vulnerabilities. Ethereum's expressive design enables more sophisticated applications but requires careful auditing. Bitcoin is increasingly adding sophisticated contract features, but through careful, incremental improvements that maintain security and decentralization. The philosophies reflect different priorities: monetary store of value versus computational platform. Future of Bitcoin contracts. The future of Bitcoin contracts is vibrant with ongoing research and development. Several trends are clear. Layer 2 proliferation will continue with Lightning Network adoption growing. New channel designs like L2 improving efficiency, channel factories enabling better scaling, and protocols like RGB and Taro bringing token and DFI capabilities. Enhanced privacy through Taproot adoption will make complex contracts indistinguishable from simple payments. CoinJoin implementations will improve transaction unlinkability. Cross-input signature aggregation will enhance privacy and efficiency. Covenant proposals will likely activate in some form, probably starting with conservative designs like CTV that enable clear use cases without introducing excessive complexity. Successively more powerful covenants may follow if the conservative versions prove safe. Improved multi-signature through continued adoption of MU-SIG2 and key aggregation will make collaborative custody more efficient. Integration with HTLCs will bring sophisticated financial contracts to Bitcoin with strong privacy. Oracle infrastructure will mature, providing reliable attestations for contracts. Scriptless scripts and adapter signatures will enable complex contract logic without revealing it on-chain, improving both privacy and efficiency. Research continues on zero-knowledge proofs for Bitcoin, potentially enabling privacy-preserving smart contracts. Cross-chain atomic swaps and interoperability protocols will connect Bitcoin with other networks. Developer tools and libraries will make Bitcoin contract development more accessible. The BitVM proposal suggests ways to enable arbitrary computation verification on Bitcoin through a different paradigm. All these developments maintain Bitcoin's core principles while expanding its capabilities, demonstrating that Bitcoin can evolve to support sophisticated applications without compromising its foundation as secure, decentralized digital money. Thank you for your attendance. Please consider subscribing to the channel.